Imagine a scientific rule so ironclad that it won a Nobel Prize in the 1950s and just sat completely untouched in textbooks for 70 years.
Right, like a fundamental truth of physics that entire generations of researchers just built their whole careers on.
Exactly. Now imagine a single photograph just tearing that fundamental truth to pieces. Welcome to the deep dive. Today, we are looking at this incredibly groundbreaking report sourced from Physical Review letters, and it's detailing this completely unexpected phenomenon observed in superconductors.
It really is the ultimate scientific plot twist.
Yeah. And our mission today is to figure out how this miniature quantum laboratory just managed to capture the secret hidden dance of these particles
Mhm.
and why this microscopic discovery could just radically transform our global technology grid.
What's fascinating here is that you have decades of brilliant minds assuming a certain mechanism works one way, really just because the math seemed to check out.
Right, and they just didn't have the tools to look any closer, did they?
Exactly, nobody possessed the tools. Then, someone finally builds a camera sensitive enough to snap a picture of the actual atoms, and the universe reveals that things are, well, vastly more complex and much more coordinated than anyone ever thought. We are actually looking at a massive missing piece of a major quantum puzzle.
Okay, let us unpack this. Before we get into the broken theory and this fancy new quantum camera, we really need to establish the baseline for you, the listener. We're talking about superconductors, which, it sounds incredibly futuristic, but the core problem they solve is something you experience every single day, which is electrical resistance.
Yeah, think about the charger for your laptop or your phone. When you plug it in, electric current flows through those copper wires.
Right, but those electrons aren't just traveling down some empty, clear tunnel.
No, not at all. They are navigating this dense, chaotic forest of copper atoms. And as they move, the electrons are just constantly crashing into those atoms. They scatter, they bounce completely off course, and they lose energy.
And that lost energy is released out into the environment as heat, right? Which is why your phone gets hot.
Precisely. It's a massive inherent inefficiency in, well, almost all of our modern technology.
So if we use a driving analogy, standard electricity is like trying to drive a semi-truck through a crowded downtown street during rush hour. You're constantly hitting the brakes, you're swerving around obstacles, burning fuel just to sit in traffic. You waste a ton of energy.
That's a great way to picture it. But a superconductor completely eliminates the traffic. When you take certain materials and you cool them down to incredibly low temperatures,
Really close to absolute zero.
right, close to absolute zero, they undergo this profound phase change. The electrical resistance doesn't just decrease, it just vanishes entirely. It hits mathematical zero.
Wow, zero. So an electric current could just flow through a superconducting loop for billions of years without losing a single fraction of a watt.
Exactly. To use your driving equivalent, it would be as if the downtown buildings, the pedestrians, the other cars suddenly just align themselves into a perfectly frictionless open highway. You never have to tap the brakes. You just glide.
You just glide flawlessly to your destination. But the great mystery of mid-20th century physics was trying to figure out the actual mechanism behind that glide.
Yeah, how did the electrons suddenly stop crashing into that forest of atoms? And that question was seemingly answered back in 1957 by the BCS theory.
Named after the physicists, right? Bardeen, Cooper, and Schrieffer.
Yep, and they later won the Nobel Prize for it.
And this is the theory that just got totally upended. So let's dig into what the BCS theory actually claimed. Why did they think the electrons stopped crashing?
Well, they realized it basically came down to a buddy system. Under normal conditions, electrons have the same negative charge, meaning they naturally repel one another. They want to be as far apart as possible.
Right, like magnets pushing away from each other.
Yeah, exactly. But the BCS theory proposed that at these extreme sub-zero temperatures, the environment changes the rules. As a single electron moves through the grid of atoms in a metal, its negative charge slightly pulls the positively charged metal ions inward.
Okay.
So it creates this tiny microscopic distortion. It's like a wake of concentrated positive charge trailing right behind the electron.
Oh, like a boat moving through water, leaving a physical ripple behind it.
Yes, exactly like that. And because that ripple is positively charged, a second electron is suddenly attracted to it. The second electron basically surfs the wake of the first one.
They link up.
Yeah, they become inextricably linked into what we call a Cooper pair. By pairing up and moving together through these wave-like distortions in the lattice, they find a way to navigate that chaotic forest of atoms without ever scattering.
Okay, that makes sense so far. The environment forces them to carpool, and the carpool lane has zero speed limit. But, there was a major assumption baked into this BCS math, wasn't there?
Oh, a monumental assumption. To make their equations actually work without the math just breaking down, Bardeen, Cooper, and Schrieffer had to assume that every single Cooper pair in the material acted entirely independently.
Wait, independently?
Yeah. The theory explicitly proposed that one pair of electrons completely ignored all the other pairs around them.
Wait, I have to stop you right there. If you have millions of these pairs crammed into a dense piece of solid metal together, and they are all leaving these physical wakes of positive charge, how is it physically or statistically possible for those wakes not to interfere with each other?
It sounds crazy, right?
Yeah, it seems highly counterintuitive to assume they just ghost through each other's ripples.
Well, what's fascinating here is that many physicists harbored that exact same skepticism for decades. It is totally counterintuitive.
So why did everyone accept it?
You have to remember the technological limitations of the era. They had absolutely no way to look inside a solid chunk of metal and observe individual electron pairs to see if they are actually interacting. Okay, so because the math worked out for the final result, they just went with it.
Precisely. The BCS math successfully predicted the zero resistance outcome, so the assumption of independent pairs just became accepted gospel. It was treated as a fundamental truth simply because testing it was physically impossible.
Right, because looking at actual electrons moving inside a solid metal is just, well, it's too dense and too fast. Which leads us perfectly into how physicists recently decided to actually test this assumption. They had to stop trying to look at the metal entirely.
That's right.
Which brings us to this new breakthrough from physicists at the CNRS and the Flatiron Institute. They built a miniature laboratory, basically a completely artificial stand-in for the metal.
They built what is known as a Fermi gas. So instead of dealing with the chaotic density of a solid superconductor, they filled a vacuum chamber with a really highly controlled gas of lithium atoms, specifically an isotope called lithium-6.
Okay, wait, why lithium? I mean, what makes a gas act like an electric current in a solid wire? It comes down to the fundamental categories of particles in quantum mechanics. Both electrons and lithium-6 atoms belong to a family of particles called fermions,
Okay.
and fermions are governed by the Pauli exclusion principle, which is really just a fancy way of saying no two fermions can occupy the exact same quantum state at the same time.
Got it.
Because they belong to the same family, under the right conditions, a sparse gas of lithium atoms will perfectly mimic the quantum behavior of a dense crowd of electrons. The lithium atoms will even form pairs, mimicking those Cooper pairs we talked about.
So it basically gives scientists a much larger, much clearer, and like a highly controlled sandbox to study the phenomena.
Exactly.
But to get that gas to enter a superconducting state, they had to drop the temperature. I mean, I've read about absolute zero in physics textbooks, but how cold did they actually have to get this lithium gas? Like, how does it compare to the vacuum of deep space?
Well, the vacuum of deep space is actually quite warm by quantum standards.
Wait, really? Deep space is warm?
Yeah. It hovers around 2.7 Kelvin, mostly due to the cosmic microwave background radiation left over from the Big Bang. The researchers cooling this lithium gas had to go much, much colder. They brought the gas down to just a few billionths of a degree above absolute zero.
A few billionths of a degree. That is mind-blowing. It's quite literally one of the coldest localized spots in the entire universe, and it's sitting right here in a laboratory on Earth.
Yeah. It's incredible. They achieved that through this amazing combination of laser cooling, where you use momentum of light to actually slow the atoms down, and evaporative cooling.
Evaporative cooling, like
Yeah.
sweating.
Basically, yeah. You essentially let the hottest atoms sweat off, leaving only the coldest behind. You really have to get it that cold to completely eliminate thermal energy.
Because if it's warm, they move around too much.
Exactly. If there is heat, the atoms jitter. And if they jitter, you just can't get a clear picture of them. So by stripping away that thermal energy, the atomic jitter stops, the lithium fermions pair up, and the stage is finally set for observation.
Okay, here's where it gets really interesting. They had the frozen gas, they had the simulated Cooper pairs, but they needed a way to photograph them without introducing heat back into the system, right? You can't just use a flash camera.
No, definitely not. And this is the real triumph of the experiment. They used a brand new imaging technique involving optical lattices.
Optical lattices, what is that?
They fired these overlapping laser beams into the chamber to create a grid of light. Think of it like a microscopic egg carton made of pure energy.
Oh, wow.
Yeah, so the cold lithium atoms get trapped in the dimples of this light carton. And once they were pinned in place, the researchers flashed them with another highly specific frequency of laser light.
And that flash caused the atoms to fluoresce, right? They scattered photons back into a high-resolution microscope lens.
Yes, and they finally had the actual data. Not an artistic rendering, not some pop science graphic. An actual pixel-by-pixel map of the fluorescence of these atomic pairs trapped in the optical grid.
So they could see the exact spatial distribution, the actual positions of every single pair of atoms.
They could.
And when they looked at that map, what did they see? Did the pairs just ignore each other like the 70-year-old BCS theory claimed?
Not at all. And the source material actually quotes the researchers describing this data. Instead of acting independently and randomly, the pairs behave like synchronized dancers on a crowded stage.
The synchronized dancers?
Yeah. The map showed a highly distinct repulsion pattern. The pairs were actively interacting with their neighbors, mutually pushing away from one another to maintain this highly regular, incredibly precise distance.
So if we return to the crowded room analogy, it isn't a bunch of blindfolded people just wandering around and completely ignoring each other. It is a highly choreographed waltz.
Exactly. Every single pair is acutely aware of where the other pairs are, and they shift their positions to make sure they don't bump into each other. They maintain an exact radius of personal space.
That is stunning visual evidence. This synchronized dance, this active repulsion between the pairs, it just completely contradicts the foundational assumption of the BCS theory.
It really does. The pairs definitely influence their neighbors. This is that massive piece of the puzzle that remained invisible for 7 decades.
But, seeing the pattern in the optical lattice is one thing. In the realm of quantum physics, you have to prove mathematically that what you are seeing is an actual physical law, right? Not just some trick of the light or a camera glitch.
Yeah, you absolutely do.
So how did they verify that this waltz was real?
Well, you bring in the supercomputers. To ensure these observations were rock solid, theoretical physicists had to build massive quantum simulations.
Okay.
They fed the known laws of quantum mechanics into the computers, introduced this new mathematical concept of active pair repulsion, and just let the digital simulation run to see what kind of spatial map the computer would predict.
The moment of truth. Did the complex calculations actually reproduce the physical photographs?
Flawlessly. The digital prediction matched the experimental snapshots of the optical lattice down to the pixel. Yeah, the mathematical simulation of how the particles should behave perfectly aligned with the photographs of how they actually behaved. The repulsion pattern is undeniably real.
So the BCS theory really was broken.
Well, we should clarify that this doesn't mean the old BCS theory is entirely useless. It still does a really good job explaining the basic formation of a single pair via that positive wake we talked about earlier.
Right, the boat wake.
Exactly. But it is definitively incomplete regarding the larger macroscopic behavior of the material. To truly understand how the magic power of superconductivity functions at a system level, you absolutely must account for the synchronized dance.
So what does this all mean? We have this new map of synchronized quantum dancers in a lithium gas colder than deep space. It is a monumental achievement in experimental physics, sure. But let's ground this. How does this translate to the real world? Why does understanding this tiny waltz matter to you, listening right now?
It is the first major step toward the holy grail of modern technology, which is the room temperature superconductor.
The room temperature superconductor. Because currently, we have to freeze them, right?
Right. Earlier, we noted that to make a superconductor work, you have to cool it down to extreme temperatures to stop the thermal jitter. Currently, the absolute best high-temperature superconductors we have engineered, and high temperature in physics is a highly relative term, they only maintain their zero resistance state at about minus 196 degrees Celsius.
Minus 196, which is the temperature of liquid nitrogen.
Exactly.
I mean, that might be fine for a highly specialized medical MRI machine in a hospital, but it is definitely not something you can build into your smartphone or string along 100 miles of power line.
Right. The infrastructure required to cool power grids with liquid nitrogen on a global scale is economically and practically impossible. But if we finally understand the exact mechanics of how superconductivity works...
If we fully decode the physical rules governing this new synchronized dance...
Yes. If we decode that, material scientists can start playing offense. Instead of just testing random alloys and hoping for the best, they can specifically engineer brand new atomic lattice structures from scratch.
Oh, I see.
Structures that are designed to artificially lock those Cooper pairs into their waltz, even when the thermal energy of the environment increases.
They can essentially build a dance floor that forces the dancers to stay in rhythm, even at room temperature.
Yes. And if we achieve a room temperature superconductor, it radically transforms modern civilization overnight.
How so?
Well, let's look at our electrical grids. Right now, a power plant generates electricity, and as it travels across hundreds of miles of transmission lines, a massive percentage of that energy is simply lost as heat due to the resistance of the wire.
We burn fossil fuels just to heat up the air above our power lines.
It's a devastating waste. But with room temperature superconducting wires, transmission loss becomes zero.
Zero loss.
None at all. You could build a massive solar farm in the middle of a sun-drenched desert and transmit that power across an entire continent to a cloudy, major metropolis without losing a single watt of energy in transit. It fundamentally solves global energy distribution.
And, the applications for computing are just as staggering.
Yeah.
The bottleneck for how fast our processors can run isn't really just about shrinking transistors anymore, is it? It's about heat.
Exactly. The processors get too hot because of electrical resistance. If you utilize superconducting chips, they generate zero electrical heat.
So no more cooling fans.
Right. You could run incredibly powerful quantum computers, massive AI server farms, or even just your everyday laptop at unimaginable processing speeds without ever needing a cooling fan.
Or think about transportation.
Oh, definitely.
Right.
The magnetic fields generated by frictionless superconductors are so powerful and efficient that magnetic levitation trains could become cheaper and faster than domestic air travel.
So this tiny observation in a vacuum chamber, this realization that the Cooper pairs are actually paying attention to each other and actively pushing away, is basically the blueprint for a sci-fi future.
It is, because before you can build the machine, you have to fully understand the physics. For 70 years, we were trying to build the future using an incomplete blueprint. We were missing a critical structural dynamic, and now we finally have those missing pages.
It is genuinely staggering to think about the technological domino effect here. But, the scope of this deep dive doesn't stop just at electricity or superconductors. Because this entire experiment, the cooling, the lasers, the optical lattices, the camera, it really opens up entirely new frontiers of research.
If we connect this to the bigger picture, the lithium Fermi gas they utilized wasn't just some clever trick to solve the superconductor problem. It is actually a fully programmable quantum simulator.
Right, like a perfect simple sandbox.
Exactly. By refining these brand new camera tools and optical lattices on this relatively simple lithium gas, researchers have essentially invented a new high-definition microscope for the invisible world.
They didn't just take a photo of one thing. They built a tool that can take photos of things we haven't even thought to look at yet.
Precisely. Now that they have proven this fluorescence imaging technique works on fermions, they can start tweaking the sandbox, they can adjust the magnetic fields, they can change the intensity of the lasers, and basically force these atoms to mimic far more complex and mysterious states of matter.
What kind of states of matter?
Well, there are theoretical materials at the quantum level, things like strange metals or quantum spin liquids, where electrons actually act as fractions of themselves that we barely possess the language for, let alone understand.
And we couldn't study them before because, just like the Cooper pairs inside a solid metal, they were just too dense and chaotic to observe in nature.
Right. But inside the programmable vacuum of the Fermi gas, we can isolate those strange quantum states atom by atom. We can actually map their behavior. Inside those bizarre complex systems might lie the foundational physics for the next massive technological innovations.
Things beyond even room temperature superconductors.
Exactly. Perhaps the key to perfectly stable, fault-tolerant quantum computing is just hiding in a quantum spin liquid somewhere, waiting for this camera to map it out.
It really makes you wonder how much we are currently getting wrong about the universe just because we haven't invented the right lens yet.
And that is the ultimate beauty of the scientific method. The moment you become comfortable, the moment you think the textbook is finished, a new tool is invented. You look through the new lens and you instantly realize you were only seeing half the picture.
Which brings us to the close of today's deep dive.
Yeah.
We have covered some incredible ground today. We started with a 70-year-old Nobel-winning assumption that seemed absolutely unshakable. We explored the physics of a miniature lithium gas laboratory cooled to a billionth of a degree above absolute zero.
Yeah, and we witnessed the visual proof of synchronized quantum dancers, these particles actively repelling each other in a highly coordinated waltz.
A tiny microscopic choreography that could one day literally power your entire city, run your devices, and span the globe without wasting a single drop of energy.
So I'll leave you with this. If a Nobel-winning theory, accepted by the brightest minds for 7 decades, completely missed this highly coordinated dance of particles, what other seemingly random or independent systems in our universe are actually moving in secret, synchronized choreography right under our noses, just waiting for us to turn on the lights?